All right, we got ourselves a lab day today. And today we are looking at determining the spring constant K for a spring. So we have a spring here, and we are going to vary the mass and therefore its weight, the force due to gravity. We're going to measure how much the spring extends. The extension is going to be its length minus its original length. And we're also going to measure the period of oscillation. If we set the spring mass system in motion, we're going to time 10 oscillations, calculate the time of one oscillation, and then calculate the time squared. So the time of one oscillation squared. Theory suggests that the period of oscillation is equal to 2 pi times root m over k. So by squaring everything in this equation, we get this. And so if we plot t squared on the y-axis against m, the mass on the x-axis, then the slope of the best fit line, which represents the trend in the data, we can set equal to 4 pi squared over k. So the slope will equal 4 pi squared over k when we plot time squared against mass, and we can solve for k. Theory also suggests that the force in a spring is equal to the spring constant times x. And so the force in the spring is a restoring force, we say, so that if we extend the spring, the force in the spring wants to pull it back. And if we compress a spring, if there's a compressive force, then the spring wants to sort of push back the other way. And the negative sign indicates the sort of opposition of those vectors, the displacement vector and the force vector. Because theory, that's called Hooke's law, and because theory suggests force equals kx, we can make a graph of force against extension. And then it's like y equals mx, where m, the slope, this time will also be k. So we can compare our two conclusions here. As a further bit of analysis, we can calculate the percent difference in k. Like once we get an answer, how far off from each other are they? Odds are they're not going to be exactly the same, but they might be close. How close are they? We could quantify with a percent difference calculation. So that would look like once we're all done, k1 minus k2 over k1 times 100%. Okay, and that will give us the percent difference in k. I'm going to use the same procedure that I adopted yesterday for measuring my spring, which is from the very end of the spring to the very end. And yesterday it was 5.4 centimeters, but you can kind of see today that's like 5.5. So these springs, and that could be like the uncertainty, right? It's plus or minus about 1 millimeter. So today my judgment says 5.5 centimeters. So L naught point 0.055 meters is the original length of the string. 5.5 centimeters or 0.055. All right, so we'll start. Remember, this is a 50-gram mass hanger, but these are all 100-gram masses, I'm pretty sure. So we'll start with 150 grams of mass. So that's 0.150 kilograms. I measured the extension to be 1 I'm sorry, I measured the length to be 11.4 centimeters. So that's 0.114 meters. So I'm going to rely on my virtual lab partners and my in-person students to help me calculate the force due to gravity of this mass and to help calculate the extension based on the measured length and the original length. And so somebody tell me what is the force both of weight acting down here, but also the restorative force in the spring that sort of pulls it back up. That's why it's in equilibrium when it's not accelerating. So anybody have the force right now due to gravity or the force in the spring? 1.47 newtons. We'll stick with that. 3 significant figures in this column. Does anybody have the extension? 6 or so. 0.059, about 6 centimeters, or 0.059 meters. Time for 10 oscillations. Oh, it's time for 10 oscillations. We're going to time 10 oscillations. Then it is time for that. Everybody with the stopwatch ready? Everybody a chance to get their stopwatches ready. It's like, oh, you got one. We trust you up there. You got the chalkboard. You're wearing a tie, right? Okay. It's good if we have some consensus, all right? So if you want to time right along, feel free to do so. Any 10 oscillations, that'd be the first time, right? So we'll set it in motion. Now here's the thing, we don't want it to jump, so I'm not gonna start from here. Remember, the more I pull down, the more I'm exerting a force. Now there's more elastic potential energy, right? So you just need to barely set it in motion. Now see how we both have up and down motion, but it's also like pendulum this way. We don't want it, right? So we want to try to just up and down. Still feel like we kind of went side to side there. I got 5.27. Was anybody else able to like sort of visualize things kind of going kind of faster? I got 5.2. Anybody else have any data they want to call out there? Is it close to 5.27? My way off? 4.95, 5.2. That's pretty close. Should we check it again? I mean, we could if we wanted to. 3 trials, right? Average all of that. I mean, we're already doing enough work today. Let's just check it one more time. Okay. Let's just get started. I think as we add mass, this will be less and less of a problem because there's more inertia, right? And so now it's like, it's kind of interesting, the physics, I suppose. Like, why is this slight little, off-centered? Like, if I release this and it gets a little bit of motion left or right, that sort of effect becomes magnified at each, sort of oscillation. That's something to do with what's called harmonic resonance, and it can be devastating. Harmonic resonance is called bridges to collapse, roofs, to cave in. I remember there was a nightclub, I think over Tampa, where it's like the rhythm of the dancing matched the harmonic resonance of the floor, and it collapsed the floor. So it's like somebody swinging on a swing, okay? And if you push them right when all of their gravitational potential energy has been converted into kinetic, right at sort of the bottom of that pendulum swing, if that's where you push them, then you're sort of matching the harmonic frequency of their oscillation. So you're adding more and more energy into that system, and that's how you can get, push somebody sort of to flip over the bar there in the on the swing set. So that's an example of harmonic resonance. I don't know if that's exactly sort of what's happening here, but you notice like the side to side sort of gets bigger each time. We'll save that exploration for another lab day, an inquiry lab. All right, we're going to get some good data here. I've got a good feeling about this. .00. You couldn't do that again if you tried. Anybody else getting data? Go with that. And that's about in between. I think we got like 4.95, 5.275. Okay, it's about 5 seconds for 10 oscillations. So how much for one oscillation? Half a second, right? 0.5 divided by 10. What's 0.5 squared? 0.25. All right, there's our first y coordinate corresponding to this x coordinate. Remember, for Hooke's law lab, we're plotting this against this. Okay, so two different experiments, but we're varying the independent variable. Okay, the mass and therefore the weight. Right, so it's like the same sort of quantity that we're varying here on Earth. You know, to kind of use it interchangeably because we all tend to be in the same gravity field. All right, so let's go up to 350, varying the independent variable here on lab day. That's why we're here. Yeah, a lot of enthusiasm. Thank you for humoring me. It's all like that. It's like this is the sad life here in the physics lab. But, you know, we vary the independent variable on lab day. All right, lots of calculations. Just kidding. All right, 1, 2, 350. And so somebody with a calculator or very adept mental mathematical ability knows that 0.35 times 9.81 meters per second squared is 3.43. That was mental math, YouTube, no calculator. And we need to know the length. (19.6) 0.196 minus 0.055 is 0.141. That's the extension. But I wonder what the time is for 10 oscillations. I know that's the question you were asking. Let's measure it. That's what we do in science. (7.66). You can time any 10 oscillations. Anybody else time that? Call it out if you got any time. 7.66, we'll go with my data then. 7.66 divided by 10, because we want to know the time of one oscillation, is 0.766. Add a couple zeros after my 0.5. 0.766 squared is 0.587 seconds squared. All right, you can anticipate a problem that we're going to have here. Ran out of room in my data table. Don't let that stop us. We already know how to do that analysis. We'll put it back on the whiteboard later. All right, we'll get this out of here too. All right, let's go up another 100 grams. I know we just varied it by 200, but so we'll put just 100 more grams. Yeah, there we go. Note how we've disturbed it. It sort of wants to do that. When we study harmonic motion and waves, it really is just kind of like this is a wave. We'll see that they're everywhere in nature. You know, like you disturb something in nature and it's going to want to tend to oscillate, like keep that energy sort of stored in the system. Like you walk by a branch, you know, and you move it, and it does the same thing, you know, but there's just a lot of dampening in that motion. So working out a general idea and then applying it sort of everywhere, right at the heart of physics. All right, so we have 450 grams. That's 0.450 kilograms. Multiply it by the strength of Earth's gravity field, 9.81 newtons per kilogram. How many newtons is that? 4.41. Remember that G, Earth's gravity field, can either be thought of as an acceleration due to gravity, meters per second squared, but it's also how many newtons of force act on each kilogram, newtons per kilogram. So that's just another way to think about the units of G. The length of this spring is starting to rival the length of my measuring device. I think yesterday we stopped at 550, right? I mean, I think we added some additional just sort of qualitatively. We'll try to extend it further here. 20. 23.6. The length is 0.236, and so 0.236 minus 0.055 is 0.181. What's the time of 10 oscillations, though? Trying to give everybody a fair chance to time whatever 10 oscillations they want to. I always count from the bottom to the bottom. So it's like once it's here, that's where I start counting. 1, 2, every time it's the bottom. But you might be counting from the top. But those are really the only two sensible places to count from. It's like every time it passes through the middle of its motion, I'll count. You know, that's tough to judge. I got 8.64. Anybody get anything that corroborates that or invalidates that? It's like, no, you're way off. Or, oh, yeah, 8.64, something like that. Feel free to call out your own data. We can publish it here. 0.864. I'll do that one. Now you all square it. If I already called you out. This one. 0.74 seconds squared. 100 more grams of mass into the spring mass system. Pop quiz. Everybody just got right. How could we check whether or not we have exceeded the elastic limit of this object, of this spring?
We remove the weight from the spring.
Well done. You passed. Everybody else did. All right. I'll take break later. 1, 2, 3, 4, 5. Gotta be quick. Gotta be quick with the pop quiz. Competitive pop quizzing. It's like only one student gets the marks. Everybody else is in competition with each other. Everybody else fails. I need to call up the rough class, huh? All right, so we're at 0.550. And 0.550 times 9.81. 5.40. If that were a pop quiz, I think a lot more people would be answering. Now we got to get the length. .281 minus 0.055. 0.260. 226. Okay, no problem. Answer covered in chalk. My calculator. Oh, chalk stuff. All right. I like my chocolate and my hydroronal chalk. Time for 10 oscillations. As the hypnotic motion of the spring mass system mesmerizes you, let's consider how greater mass means greater inertia, means greater tendency to resist change in motion. So note how it's been taking longer and longer for this to oscillate as we've increased the mass. That kind of makes sense. If you kind of go through what inertial mass means, right? It's inertia, it's a tendency to resist change in motion. Note also the problem of swaying side to side is kind of minimized for the same reason, right? It wants to kind of stay put where it does as we increase the mass. I got 9.43. Anybody else get anything?
I got 9.53.
9.43. We'll go with your time. Now my words, we'll publish your data up here to call it out. 9.53. I'll do the hard part, and then you guys square it. 0.953. Your turn. 0.908. You know, thanks to me, you're able to do that. 1, 2, 3, 4. Two hundred grams. Here, let's get crazy here on that day. Note, I no longer have an adequate measuring device. I'll need something more appropriate for the job. A meter rule. That's 750 grams of mass, or 0.750 kilograms. The beauty of the metric system, all base 10. 0.750 kilograms times 9.81 newtons per kilogram is
7.36.
7.36 newtons of force acting down. Also 7.36 newtons of force in the spring, a restorative force, right? Pulling back up on it, right? So it's in equilibrium. My handy meter rule. I'm starting on the 2 centimeter mark. It's just easier for me to sort of read that. So from 2 up to 30, 7.2 is what? 35.2. 0.352. 0.352 minus 0.055 is 0.29 something what? 0.297. About 30 centimeters of extension from the original length of the spring. Time for 10 oscillations. Here we go. I got 11.03. Anybody else want to publish their data? Call it out. How are we doing on time?
I got 10.58.
10.58. I got 11.03. Anybody get closer to?
Yeah, I got 10.58.
Say yours again.
10.58.
0.58, 0.68. We'll go with yours because it's kind of in between. You know, I got 11.3. So 10.68. If you want to, right, like you at home, you could say, well, I'm going to average all those times I just heard. You know, I think that's a good way to sort of, that's fine. Okay, you as the experimentalist doing the experiment, use your judgment to say, this seems the most reasonable. All right. And again, when you go into industry, when you do research, it really is up to you to say, I want the strongest experiment, I want the best results possible and what makes sense to me for how to collect this data. And that is the hard work of science, getting better and better experiments, removing all the systematic errors that are bound to be there. Okay, we don't always know what they are at first. We sort of, look at the data and go, something's amiss here. Just yesterday, they announced the awards of the Nobel Prize in Physics. Roger Penrose, congratulations. I'll show you a book I got back there that Penrose wrote. He was a collaborator with Stephen Hawking for years and years, helping kind of, really understand black holes, and then two other researchers that really helped discover Sagittarius A star, the supermassive black hole at the center of our own galaxy. So congratulations there. All right, I'll do this 1.1068. Now, it's going to be hard to sort of plot that. We could either decide to round this to 7 or like add a 0 onto the end of these, but be consistent, right? So if I've got 4 digits here, I want 4 digits also here, so I could add like a 0 onto the end of these and have 4. But odds are I'm not going to be able to I'm not plotting this anyway. I'm going to plot this quantity. So it's kind of up to you, but do be consistent with how you present your data in a data table for the same number of digits. Did I do that right? No. 1.068, right? Not bad. All right, what's 1.068 squared? Still about 1, right? Anybody? 1.068 squared. 1.011. 1.011. I'll just leave it like that. 1.01. Okay.
I got something. I got 1.4.
1.068 squared. 1.14, right? One, two, three, four, 5. We got 750. We'll jump all the way up to 950 right now. I am somewhat worried about the spring, but we'll.
Yeah.
Okay. There we go. Now it's becoming possible, I think, for half of the lab to see the spring mass system anymore to collect the data. I think we're still in view here, but at the bottom of the frame, let me adjust this slightly. Be mindful of my virtual students wanting to follow along at home. We've got 1, 2, 3, 4, 5, 6, 7, 8, 950 grams of mass here on Earth. Should have written this a bit smaller. All right, so now we're going to go. I need one of those chalkboards that slides up like this. Have more chalkboard space. Or just even raising these chalkboards up a bit. Okay. Suggestions? Just fit it underneath there, you're saying? One more data point, just end at 6. I want it to exceed a kilogram, though. Everyone else is like, yeah. We all have to say it and go, like, yeah, we exceed a kilogram, though. We want one more after. This is 950. That's kind of what I was thinking too, but then I'm like, I'm looking at it, it's like, I think what I just need is.
You could try the other chalkboard.
Looks so bad. The other chalkboard. Yeah, we could put it over there on another chalkboard. I kind of like that. Here's what I think we should do. And we'll do this democratically, keeping in mind that my vote is n plus 1, where n is the number of students voting. Let's just go and exceed a kilogram for everybody that wanted to do that, and squeeze that data point down here, and we'll just call it a day with 6 data points. There's a little bit of disappointment in the lab for students that wanted 7 data points, but I'm sorry. Bigger chalkboard. Smaller writing. I need smaller writing. I won't blame the chalkboard here. All right, so now we've got 1,050. Forget 950, 1,050. Yeah, that's the final data point of the day. That's something I'm excited about. Sorry that it's all downhill from here for the rest of your day, as you have physics first block. You're like, I gotta go. Boring English class, history. Yeah, I said it. Yeah, I'm on record. So now we've got 1, right? We've exceeded 1 kilogram. All right, but what does 1,050 grams look like? So that's like, we do the decimal point over 3, so it's like 1 point, and then where's the 50 go? Not 1.5, right? It's 500, so it's 1.050, right?
Mm-hmm.
And if you've got really good eyes, you can maybe read that. 1.050 kilograms times 9.81, got to be about 10 or so. But it's exactly
10.30.
10.30. And 0.30. The length now. The total length. Same strategy. 2 is 52 even. So that is 50 centimeters or 0.500 meters. Like exactly. So 50 centimeters minus 5.5 centimeters is 44.5 centimeters. 0.445, that is that right?
Yeah.
0.445 meters of extension from its original length. Wow, it's been 6.5 minutes since the last data point. All right, that's too long in between data points. All right, here we go. Final data point of the day, final data collection. The rest is calculations from here on out. I got 12.66.
I got 12.83.
12.83, 12.66. Any others? Any others? 12.83. 1.283 squared. So we'll just say 1.65, right? 1.65. We are somewhat mindful of this is the data we're actually plotting, and so how precisely can we sort of read off our graph depends on sort of what our scale is, but we'll be able to like sort of accurately say, oh, it's a little bit, 1.646, like that 0.6, can we accurately say this? We'll just round it to the hundredths place. All right. I think we've probably exceeded the elastic limit here. So remember, we say that the spring obeys Hooke's law when the force is proportional to the extension. But we might have sort of permanently deformed it at this point. So if we observe like a trend line in the data, but then it seems like this point seems anomalous, like it doesn't quite fit the trend that we've established, it could be for that reason that we've already sort of changed the spring. Let's change the spring a little bit more, since we got 1,050 kilograms, so that's good, I think, in terms of the data that we're going to collect. But let's qualitatively just observe if we added 1,250, so 1.25 kilograms. And you can see that I definitely, like I can by inspection look at this and go, this is a plastic deformation, right? You can kind of see it unwinding. But if we can add 1,250, we can add 1,450. Oh boy. All right, and this is where safety dictates that we collaborate. You can see that this coil, okay, which was like a perfect circle wound twice, completely uncoiled, right? As we added, almost 1.5 kilograms to it. Again, by inspection, you can see like that is a plastic deformation. And your question yesterday was like, do we ever maybe compress it, put a compressive force on it, like put it between two books and come back, after the weekend and maybe would it ever be back the same? Again, my hypothesis is I doubt it. Like this is not going to ever kind of be the same again, but it's testable, right? So here we see evidence of a plastic deformation. Was it already sort of on its way like this by like this data point? Again, we might look at the data and go, everything's in a nice trend, and then I get this one that's like kind of way off. Like I had this nice linear trend, and then the last data point seems anomalous. Okay, and we have a good explanation as to why that might be the case, if indeed that's what we observe when we go to plot this. All right, so as a quick sort of review here, how can we get to work here and report our claim? What is the spring constant of this spring? Or was the spring constant of the spring? Beginning of the lab, we will first plot force against the extension, and the analysis there is simple. The slope of the best fit line is the spring constant K, because the rise is in newtons, the run is in meters, and K tells us how many newtons of force to stretch the spring out 1 meter, right? So it's like force per distance. How many newtons of force to stretch the spring out 1 meter? That captures like the stretchiness of the spring. Just think about it. If it took a lot of force to stretch it out 1 meter, that'd be a really stiff spring, right? It takes a lot of force to stretch it. If it doesn't take so much force to stretch it, it's a very stretchy spring. So this really does tell us like the stretchiness of the spring. That's what K kind of really tells us. Additionally, what I had erased here, we will plot time squared, measured in seconds squared, so always be sure to label your axes, against the mass measured in kilograms. And again, you'll find that that's linear, right? As we increase the mass, the time squared also increased. And so there's a linear trend there. The analysis here is a bit trickier, but it's one that's a little bit familiar to us by now, having worked with the pendulum experiment. The slope of our best fit line is equal to this term, right? And again, it's just looking at the equation of a line. Y equals mx, m is the slope. It's not confusing at all when like your x is m, right? This is the slope m. So just know that we set the slope equal to this term, I think K will be your only unknown. You can solve for K. As a final step, you can compare those two conclusions. K1 minus K2 over K1 times 100%, that'll be the percent difference in K. We're hoping for a very low percent difference, right? Like if we did a good job, we want these K values to be very close together because it's the same spring. And so if the percent difference in K is like 1%, then you get a 99 on your, lab grade. If the percent difference is 50%, you get a 50F. I think that's a fair way to read it. Okay. Just kidding. All right. Just do the lab work, right? And practice, plotting the sensible scales on your axes, good. Best fit line, equal number of points above and below the line. So there's a good balance there. Choose points that are not data points on your line that intersect the gridding of your graph paper to do the slope calculation, and try to find points as far away from each other as possible. Okay. If you find points that are really close together, that will also cost you a mark in like terms of ACE paper 3. All right, so good graphing rules. All right, so that's it for lab day today. I'll let you all get to work on it.